Okay, so last time we started thinking about, we actually started the class before last time, but basically we are continuing to think about what happens to the heat given to a system. And our starting point for all of this, as usual, is the first law of thermodynamics that goes as du is equal to delta Q plus delta W. And we are interested only in pressure volume work for the moment, so we can write it down as minus PdV. du is equal to delta Q minus PdV. So I'm going to recap some of the concepts from last time. Some of you will think there is nothing new here, which is great. Some of you, clearly from the range of questions I was getting asked on Slack and direct messages, did not really capture any of it. So it's important that I go again and rephrase it. And some of you asked me questions on Slack asking, one of you asked, what is the relation between heat and enthalpy? And my answer on Slack was, please go watch the video. And I might have come across as brash, but really that's what we talked about. If you're paying any attention in class or watching the video, you should not have asked that question. So please watch the video. And if it's still not clear, then you can ask me. But for the sake of that student and others, I will recap things. So let's think about two scenarios. We have a system. In this, we have a system made up of gas molecules, and we have identical copy of this, where also we have gas molecules. One of these is a constant volume scenario, and the other one is a constant pressure scenario. Why do we care about these two? Because these two are the natural setup in which many chemistry experiments are carried on. Later, we will see there are other setups also. You could even have a constant enthalpy scenario. Those of you, there is at least one geology student in the class. Is Cosmo here? Cosmo's not here. There's at least one geology student. If you're studying volcanoes, how they form, how they erupt, then it's a constant enthalpy process. You might be interested in other things. But for now, we are talking about these two. So in both of these, what we are doing is to put heat into the system. So this is delta Q. Some heat is being given to the system. And the question is, what does the heat do to the gas molecules? So in this first case, this lid over here is tight. The gas cannot move up or down. In the second case, the gas can move up or down. So in the first case, all of the heat goes to gas molecules energy. In the second case, some of the heat is used to do work against surrounding, right? Because this thing can go up or down. As you're giving heat, it's probably going to expand and push it up against surrounding. So in this first case, we can see it's a constant volume process. So du is equal to delta Q minus PdV can be written as du is equal to delta Q minus 0, because dV is equal to 0. It's a constant volume process. Or du is equal to delta Q. So we get this very interesting relation that all of the heat given to the system goes into increasing the internal energy of the system. And this is differential form. We could also think of an integrated form. If you have given Q heat to the system, all of it goes into changing the internal energy of the system. The question we ask for the second case is, what happens to the heat over here? Clearly, it's not equal to delta U, because some pressure volume work is also being done. So it's something else. And here that something else happens to be H, the enthalpy, which is defined as H is equal to U plus PV. So this is the thing you need to remember. Anytime enthalpy confuses you, it's capturing what does the heat do in a constant pressure process. So in this case, we can write it down as du is equal to delta Q minus PdV, and we can no longer say dV is equal to 0 because something is going on. And in this case, if we start with, and if we want to prove this relation, we can start with d of H is equal to d of u plus PV, right? And that is du plus PdV plus VdP. It's a constant pressure process, so this one is going to be 0. So dH is equal to du plus PdV. And now we can use the first law of thermodynamics. Du is equal to delta Q minus PdV. And that cancels out. This is what we saw last time, that dH is equal to delta Q, right? So it's a slightly more complicated. That's why students also get confused, but it really shouldn't confuse you. So this is what you should remember. Delta Q is equal to delta U for a constant volume process, and delta Q is equal to delta H for a constant pressure process. From this, the heat capacities follow naturally, because heat capacity at constant volume is defined as the amount of heat you have to give to a system in order to cause the temperature to change by a small amount at constant volume. And we just showed that at constant volume, delta Q is equal to delta U, right? Therefore, this is equal to partial U by partial T at constant volume. Heat capacity at constant pressure is the amount of heat you need to give to the system to change the temperature by a certain amount at constant pressure. And we just saw that at constant pressure, delta Q is equal to delta H. This is not always true. This is true only at constant pressure. This thing is true only at constant pressure. This thing is true only at constant volume. These are true. We don't need to have an ideal gas for this to be true. Okay, nowhere have we assumed PV is equal to nRT. This is true for any gas at, and so just to emphasize, this is any gas, not necessarily real, not necessarily ideal. It could be anything. So this is partial H by partial T at constant pressure. Any questions about this? No questions? Oh yeah, please.
What's the physical intuition behind like enthalpy? Like how we intuitively think about it?
This is not intuition enough for you?
I guess like at like non-constant pressure, how we do that.
You remind me of two mathematicians. Two mathematicians were talking. Let me tell you this story. Two mathematicians were talking. One of them writes a theorem, and the other one looks at it, goes like, "This is not trivial to me." And then the two mathematicians fight for 8 hours. They fight and fight and fight. And then they finally fill up the full blackboard, and the second mathematician goes, "Okay, now it's trivial to me." So it depends on what's intuitive. This is the most intuition I can give you is, and we will look at it a little bit more. Today, we are going to look at some practical, I actually have a practical problem, a real chemical reaction, in which we are going to calculate the change in enthalpy and the change in internal energy. This will give you a bit more intuition. But if a chemical reaction is purely solid, if species are solid, if the reacting species are solid and the products are solid, for all practical purposes, then enthalpy and internal energy are the same. It's really when you have phase transition going on, when there is gas being produced, liquid is changing into gas, or solid is changing into gas, or even solid is changing into liquid, that's when these terms start to differ. And the most important physical intuition is that it accounts for the expansion work being done on the surrounding. So this sounds obscure, but anytime you want intuition into enthalpy, you have to go and look at this picture, the one drew over there. Anytime you expand, the work that is being done on the surrounding, subtracted from the internal energy, becomes enthalpy. So that's what it is. And we'll work through this example and to give you more intuition. So at this point, let's try to think about Cp minus Cv. So Cp minus Cv is always positive. Why? Because the heat that you gave to the system, who answered last time? Was it Stella? Was someone sitting over there? What's your name? Stella. Yeah, Stella answered this last time, that when you're giving heat to the system, some of it is, not all of it is used up to heat the system, right? Some of it is being lost to do work against the surroundings. So naturally, we expect that in this case, you get less bang for your buck, right? You give certain amount of heat, not all of it changes the temperature. Some of it is just lost doing work against the surrounding. So we know intuitively that Cp should be more than Cv. In order to increase temperature of a system by 1 degree Celsius, 1 degree Kelvin, more heat is needed for constant pressure process than constant volume process. This is intuitively clear that it should always be positive for anything. One of the problems that I posted on Slack was how much is it? Can we actually write down a number for how much does it exceed? How much positive is CP related to CV for a constant, for an ideal gas? So for an ideal gas, and hopefully some of you tried it, I'm going to work through the solution for that right now. So for an ideal gas, let's try to actually write down CP minus CV. So we had, let's call this as equation number 3, the relation for CP and CV. And let's call this as 2A and this as 2B. Delta Q is equal to delta U for constant volume is 2A, and delta Q is equal to delta H for constant pressure is 2P. Okay, so CP minus CV is, let's use equation 3. So equation 3 tells us that this is partial U, oh, we are talking about CP minus CV. So this is going to be partial H by partial T at constant P minus partial U by partial T at constant V, right? This is true for anything. We have not made any assumption yet. This is true in general. True in general. What should we do next to proceed with our derivation? Any ideas? Right? Even before that, first let's just write down the formula for H. H is equal to U plus PV, right? That's true in general. So we use H is equal to U plus PV. Therefore, CP, there are many ways to do this, of course, becomes partial U plus PV by partial T at constant pressure minus partial U by partial T at constant V. At this point, if you're not careful, and this is where one of you asked me before the first homework, why should I write down this all the time? If you don't write this in this problem, you will get a wrong answer. It's very important to specify what is being held constant, right? If you're not careful, you can really mess up. So let's split everything out. This will become partial U by partial T at constant pressure. Okay, the first term. The second term will be partial of pressure multiplied by volume by partial T at constant pressure. The third term will be minus partial U by partial T at constant volume. And again, this is why it's important to specify what is being held constant. If you're not careful, you would just cancel these two. Clearly, that's not true. These are two different partial derivatives. So we cannot do that. We have to be careful. So now, so far, we have not used any ideal gas. Okay, now let's assume ideal gas because we are talking about an ideal gas. Assume ideal gas, which is the problem here. Then PV is equal to nRT, right? So this second term becomes partial nRT by partial T at constant P. That is simply nR. So we have CP minus CV is equal to partial U. So every time I give this problem in an exam or something, I will tell you the mistakes students make at this point, and which I cut some points and then everyone gets very unhappy. So it looks just like what we wanted to prove in that problem, right? Only if we could cancel out the first two terms. They are both partial U by partial T. One is at constant P, one is at constant V. For if this was not an ideal gas, if this was a real gas, would this be equal to 0 for a real gas? It won't. We don't know how U depends on T and how depends on V for a real gas. But for an ideal gas, we know how U depends on T and V, right? So let's mark this as equation 4. I will go to next page. So equation 4 says that Cp minus Cv is equal to partial U by partial T at constant pressure minus partial U by partial T at constant volume plus Nr. Now, for an ideal gas, what do we know about U? It is proportional to number of degrees of freedom multiplied by half RT. Ideal gases' potential energy does not depend on pressure or volume. So, for an ideal gas, partial U by partial T at constant P is equal to R by 2n degree of freedom. And that is the same as partial U by partial T at constant V. This is true only for an ideal gas. For real gas, those two things won't be equal to, they won't be the same. Therefore, Cp minus Cv is equal to Nr. In the exam, in the Slack problem, I asked you to just prove proportional to R, and I didn't really get into this N, but this N ends up becoming different for diatomic gases. For gases with different structure, you have to think about the number of degrees of freedom. But the point here is that at least if you had point-like gas molecule particles in an ideal gas, Cp minus Cv will be proportional to the number of moles of the gas molecule multiplied by the ideal gas constant. So this is true for an ideal gas. This is not true in general. For other gases in general, there are more complicated relations, and we will be looking at some of them later once we get to entropy. Any questions about this? Okay. It's all easy, right? That's Karina. Karina is nodding her head very vigorously, so she's gonna nail this problem. Okay. Help us solve this, Karina. Yeah. It's okay. Don't feel happy. Just work with everyone. Let's go through this together. So we have calcium carbonate solid, and it is changing into its polymorph aragonite. Does anyone know here what's a polymorph? It's the same compound when it can take two different crystal structures. It actually matters a lot. All the biochemists and also the chemists should know what's glycine, right? It's the simple amino acid. Did you know that glycine is used as an antidepressant, but only in one polymorph? If it changes into the other polymorph, it is still glycine, and then it does not act as an antidepressant. It's useless. Same for paracetamol, your headache-causing drug. Headache-solving drug, not headache-causing drug. If it changes into another polymorph, it becomes useless. So in chemistry, especially in the drug design, in the pharmaceutical companies, they are very interested in making sure that that's why they give you labels. Don't put the drug in direct sunlight. It's gonna change it into another polymorph out of other things, and then you think, oh, my glycine will cure my depression. Next thing you know, you're getting more depressed because it becomes something else. So here we are looking at calcium carbonate, which is a simple mineral, and it is changing into its polymorph aragonite. So this is a solid. A polymorph for a crystal is also solid. Liquid is not a polymorph. So the phase transition is not to a gas or a liquid. A solid is changing into another solid, and you have been given the change in molar internal energy, which is 0.21 kilojoule per mole. So here they want you to think about the relation between the molar internal energy change and the molar enthalpy change when the pressure is 1 bar, and you have been given the mass density. So write down these numbers in the corner of your notebook or wherever, and then I'm going to remove this screen and try to solve this problem together with you. Okay. Everyone got the basic numbers? Great. So let's try to solve this problem. So this is problem 2B1. 2B1 is an example of solid to solid reaction. No gas or liquid is being formed in the process. The phase of matter stays the same. And you have been given that delta U, which is U of aragonite, it sounds like a character out of Lord of the Rings, minus U of calcite. Let's abbreviate this as U of A minus U of C, okay? I don't want to write aragonite all the time, is equal to plus 0.21 kilojoule per mole. And what we need to calculate is delta H. The problem wants us to calculate the enthalpy of A minus enthalpy of C. Why can we calculate such a thing? Because enthalpy is a state function, right? Enthalpy is U plus PV. If U is a state function and you add pressure multiplied by volume to it, you also get a state function. So how to do this? Any idea how should we proceed at this point? We can again write down the definition of H, right? H is equal to U plus PV. So let's write that down. This becomes UA plus PA plus VA minus UC minus PC minus VC. What do we know about pressure? The pressure is kept constant at 1 bar, right? So we don't have to think about PA and PC separately. So this is UA plus pressure multiplied by VA minus UC minus pressure multiplied by VC. So this is UA minus UC plus pressure VA minus VC. And this is delta U, right? We have already been given that delta U is UA minus UC. So we are getting a relation between delta H and delta U. Delta H is equal to delta U plus pressure multiplied by VA minus VC. And note, I haven't assumed any ideal gas behavior so far, right? This is exact. I have not assumed PV is equal to NRT. So in chemistry or in general, in any problem, try to avoid making assumptions as long as you just can't get any further without making the assumption, right? Push, push, push and see, do you really need to make the assumption? Okay, if you're convinced that you do need to make the assumption, then make it. State it clearly what assumption you made and then proceed. So far, we don't need anything. So let's think about delta H minus delta U. That's going to be pressure. What is the value of pressure? 1 bar is equal to 10 to the power 5 Pascal. And VA minus VC, and here I'm going to go through it quickly. We have been given the molar weight of calcium carbonate is 100 gram per mole, right? Calcium carbonate itself is not changing. And on top of that, we have been given the mass density of both phases. So we know the molar weight, which is 100 gram per mole, multiplied by VA, that's going to be 1 divided by 2 point, and this is also solved in Atkins, by the way. So if this is not clear, you can go and look at it. Gram by centimeter cube minus, for calcite, 1 by 2.71 gram by centimeter cube. So let's see if the units make sense. Gram, gram cancel. We will have Pascal multiplied by centimeter cube divided by mole. Pascal is pressure, right? So let's do a quick thing. So Pascal multiplied by centimeter cube is pressure multiplied by volume. What is pressure? Pressure is force by area. And what is volume? Volume is area multiplied by length, right? So area cancels. We are left with force multiplied by length. That is the correct unit of energy, right? So we are on right track. Dimensionality analysis is something in physics and in physical chemistry or chemistry, it's good to do all the time to make sure you're not missing out on something. And all of this will be divided by mole because we are interested in the difference. We are interested in the molar enthalpy, not the total enthalpy. Okay, so this is a simple arithmetic operation, you multiply everything. And what you get is the number as minus 0.28 joule per mole, not kilojoule, but joule per mole. Okay, if you multiply out whatever is written over there, you have to take my word for it. All of this, 2.93 and 2.71 over there. So what did we just get? We got that delta H minus delta U is equal to minus 0.28 joule per mole. We don't really know if that's a small number or large number. It probably looks like a small number, right? Joule is a very, very tiny thing. Our daily calorie input tends to be 2000 kilocalorie, which is around 8,000 kilojoules. So this is really small number as far as our intuition goes, but let's see how small it is. So let's calculate delta H minus delta U divided by delta U. So how much of a percentage difference it is related to delta U? That will be minus 0.28 joule per mole divided by plus 0.21. Was it plus? Yeah, it's plus 0.21 kilojoule per mole. This is approximately 0.1%. It's a small number. Okay. In other words, we just showed that when you have a solid to solid change, or it could have been solid to liquid, or basically if no gases are involved, for solid to solid change in enthalpy is approximately the same as change in internal energy. Does this make sense? It makes sense, right? Why did we have the concept of enthalpy? We had the concept of enthalpy because the gas can expand and do work against the atmosphere. But if you just have solids, what's going to expand, right? There will be some volume change, but a solid is not just going to expand against the atmosphere. There is some difference. It's not that delta H is exactly delta U, but the difference is small. Now, on the other hand, the problem in Atkins after this one, which I want you to go and read, considers another reaction, which is hydrogen gas plus oxygen gas mixed together to form water, liquid. So gas going to liquid. Would you expect this similar result here, that delta H is delta U? No, why? It's not just gas is changing into liquid, right? So if you think about, there's something structural going on. So if you had, on the other hand, if you had 3 moles of gas changing into 3 moles of gas, maybe they would have been similar. But something like this, where all of the gas is suddenly disappearing and changing into liquid, you will have a huge change. So Atkins, so in this case, we can write it down. H is equal to U plus PV. And if you assumed ideal gas, the change applies even if it's not ideal gas, but to get some intuition, then H is approximately U plus nRT. Therefore, delta H is equal to delta U plus delta N gas multiplied by RT, approximately. Okay, so the number of moles of gas molecules that change during the course of the reaction will directly affect the enthalpy. In the first reaction that we saw, delta N gas was 0. There was no change. We got the answer for the first problem without invoking ideal gas law. But in general, you can see when delta N gas is equal to not 0, when gas is being produced or consumed, then you expect H and U to be different. Otherwise, they are the same. And which boils down to the simple picture that H is different from U because of the system's ability to do work against the surroundings. If it's a solid, it's not going to be that much. There will be something, but not that much. Any questions about this? Please. Good question. Yeah, I believe I have to look up the Atkins exact problem, but this is a constant temperature. So look up 2B2 and what they exactly say. Yeah, so do this. Consider this as a practice problem. 2B2 in Atkins, try to do it. It's solved there already, okay? So don't look up the solution, try to solve it on your own. And if it's not solved, I will post a solution. Any other questions? Okay. So So hopefully you have gotten some intuition into what is enthalpy. Why did we need to bring in this picture of enthalpy? It is a quick way of capturing what happens to the heat given to the system when you have expansion going on in the system. Why do we need such a way? Because heat is a path function, right? Different processes will have different path heat values depending on how you carried out the heat. In thermodynamics, in physical chemistry, especially thermodynamics, our aim is always to change path functions into state functions. Okay, that's always what you want to do. Path functions are ugly; they're hard to deal with. You cannot differentiate them. You need to know exactly how things carried out. State functions are wonderful. It just doesn't matter. So that's what we did. So before I go further, again, I will re-emphasize this. For a constant volume process, the difference in this state function of heat is equal to the change in internal energy of the system. Sorry, heat being path function, and it's equal to change in a state function, which is the internal energy. But for a constant pressure process, instead of delta U, you get delta H, which is also a state function. That led us to Cp and Cv. We showed intuitively as to why is Cp more than Cv. Then we derived an expression for an ideal gas. We showed it is equal to Nr. This is true only for ideal gas. For real gases, we can derive an expression related to the isothermal compressibility. We will do that later, maybe a few lectures from now. For now, let's take a step back and go back to our favorite state function, internal energy, right? So how did we talk about internal energy for a constant composition process? We said it could be a function of temperature, volume, pressure for constant composition. If it was not constant composition, then we would have to talk about N also, right? The number of moles. Then we said that at equilibrium, we should be able to write pressure as a function of volume or temperature, volume as a function of pressure and temperature, and temperature as a function of pressure and volume, right? These are our equations of state, which apply to a system at equilibrium. Ideal gas law is one equation of state. Virial law is another equation of state. And then we showed that if we choose to do it as U as a function of temperature volume, then we get a relation du is equal to partial U by partial T at constant V multiplied by dt plus partial U by partial V at constant T multiplied by dV. And this becomes Cv, right? This is the definition of heat capacity at constant volume multiplied by dt. And we gave this a name. Anyone remembers? Internal pressure. It was pi, right? Internal pressure pi T multiplied by dV. And we showed that for an ideal gas, pi T is equal to partial U by partial V at constant T is equal to 0, and du is equal to Cv dt. For any gas, ideal or not, du is equal to Cv dt plus pi T dV. This relation is very general. It's true for anything. du is equal to Cv dt is true only for an ideal gas. The nice thing about partial derivatives in thermodynamics is, so what is really a partial derivative? A partial derivative tells you that if something is a function of 4 different things, you can calculate how it changes with respect to one of those things if you keep the other 3 constant, right? That's the whole idea of a partial derivative. Before multivariable calculus, when life was all nice and simple, we did not have to think about partial derivatives because everything depended on only one thing at a time, right? So we could just think about change of varying one thing with respect to another. In partial derivatives, when a function depends on 3 different things, we start thinking about, okay, what is the change in f with respect to x if y and z are held constant, right? We can talk about things like this. And these are very important things, right? Most experiments in life are related to partial derivatives, right? because you have some function and there are 5 different control variables, and you try to keep 3 different control variables constant and change only one variable, and you get certain property. In fact, many experiments are wrong because people are not careful about controlling what is being held constant, right? So partial derivatives are very natural to life. And the multivariable calculus is wonderful because it allows us to manipulate partial derivatives. You can calculate this one and connect it to partial f by partial y at constant x and z. There are relations in multivariable calculus that allow us to do this. And that's why multivariable calculus is such a powerful tool. So let's consider something which will seem like a bit of a tangent to you, but you will see why it's useful. Let's consider that if instead of UTV, I had some instrument that measures change in U with pressure, not with volume. Let me rephrase it. So what if you had an instrument that measured change in U with temperature at constant P? What would be the mathematical notation for such a change? How should I write it down? Partial of what over what? Any ideas? Who said? Okay, and I need to specify one more thing. P constant, right? This one. So let's say our instrument measures this. What do you do with this instrument? You say it's crap, I don't care about it, I don't have any relation for it, or can you derive something out of it, right? So this is just an example of how can we do something useful with something like this. So so the question is, what do we do with this? Okay, so where was I should get better at numbering my equations. That was 4, the last I see. Let's call this as equation number 5. So let's start with equation number 5 once again. And this is kind of counterintuitive. We are still thinking about temperature and volume, but let's see how it gets us here. So equation 5 says du is equal to Cv dt plus pi t dv, right? So let's divide both sides by dt. What will that give us? That will give us Cv plus pi t dv by dt. Now think about constant pressure. At constant pressure, if your process was happening at a constant pressure, you can take equation 6 and write down the left-hand side as partial u by partial t at constant pressure. Cv doesn't depend on what's the process, right? It's a state function. Plus, same with pi t, it's already done. And we get our partial v by partial t at constant pressure. Okay. So we have been able to connect this thing that the instrument measures with some other things. It has some information about the heat capacity. It has some information about the internal pressure. And this new partial derivative just popped up. Does anyone see what this new partial, does this new partial derivative remind anyone of something we have seen, not in this class yet, but before? Everyone has seen it. Go ahead. Go ahead. What did he say? No, even simpler, like high school simple. What is the change in volume with respect to temperature? It ends with a coefficient. What's this telling us physically? We are measuring the change in volume when the temperature is changed. What is the name for this thing? Even simpler, even simpler. Middle school. Go ahead. Huh? No, even simpler. What is the name for when something changes volume, when you heat it? What do you call it? There we go. Thermal expansion coefficient, right? Our thermal expansion coefficient, isn't that not middle school? Man, I went to a very good middle school. Okay, high school. Come on. Okay, freshman year. Okay. Without calculus, this is middle. Come on. We all know about water. Okay, let's get to this alpha in a moment. So this alpha is volume thermal expansion coefficient, which is defined as change in volume with respect to temperature at constant pressure per unit volume, right? Is alpha positive, negative? Can it change? Can alpha be zero? What happens to most materials when we heat them? They expand. So in general, alpha should be zero. Do we know of expansion? Do we know of, what's it called? Contradictions to this? Water. Yep, is the reason for life, perhaps, that water does not have alpha positive all the time. If water had alpha positive all across the temperature, almost certainly we would not be existing. We would definitely not be existing in this form, right? We might have had 8 eyes and 20 legs or something. We would look very, very strange. It is for water between 0 to 4 degrees Celsius. Alpha is actually negative, right? Water starts to contract. Ice is lighter than water. Ice starts to float on top of water. This is how life survived, right? It points. I have material scientists in the classroom. How many material scientists today? This is a question for material scientists. Do you know of a material, of a class of materials that actually has negative thermal expansion? It has a name though, that class. It's called Invar materials. Those are super cool. There is a whole class of materials which not just in 0 to 4 degrees Celsius, but over 1000 degrees Celsius, you keep heating it and the thing keeps contracting. You heat it more, it contracts more. And that's super, super cool. And the reason for that is really complicated. We cannot explain it because we know, and I mean, we'll see it in a moment. So in material science, these materials are called Invar materials, have alpha negative. And here comes the chemistry. For whatever reason, most Invar materials have iron in one form or the other. They are alloys of iron. Okay, so I think that's super cool. So can we show something about alpha for an ideal gas? Can we write down an expression for alpha for an ideal gas? We can actually write down alpha rigorously, exactly. Why? Because for an ideal gas, and by the way, let me call this as equation 7. We will come back to equation 7 after we play a little bit with alpha. For an ideal gas, PV is equal to nRT, right? So volume is equal to nRT by pressure. So if you calculate partial volume by partial temperature at constant pressure, that's going to be nR by P. Therefore, alpha for an ideal gas would be 1 by volume multiplied by nR by P. What is in the denominator? We have PV. So nR divided by nRT is equal to 1 by temperature. So we have an interesting relation for an ideal gas, that for an ideal gas, the thermal expansion coefficient versus temperature should look like this. It should always be positive, but it should go down to 0 as the temperature increases, which is quite interesting. So it's telling you, and it's kind of counterintuitive, right? Why should an ideal gas expand when you put temperature into it? But it does. And the rate at which it expands decreases as a function of temperature. But water can have alpha even negative. Invar materials can have alpha negative. So this is just a bit of aside into what is this thermal expansion coefficient. Now let's go back to equation 7. I'll let you copy this before I change the page. So now let's revisit equation 7. Okay. So equation 7 said that partial U by partial T at constant pressure is equal to CV plus pi T partial volume by partial temperature at constant pressure. And we showed that alpha, we defined alpha, thermal expansion coefficient, as 1 over volume partial V by partial T at constant pressure. Therefore, alpha multiplied by volume is equal to partial V by partial T at constant pressure. Therefore, this thing that you measured, partial U by partial T at constant pressure, is equal to CV plus internal pressure multiplied by thermal expansion multiplied by volume, which is kind of neat relation, right? You measure something very abstract, which is how does the internal energy change with respect to pressure? And you get the heat capacity, internal pressure, thermal expansion coefficient, and volume. So relations like this in thermodynamics are confusing more than anything else, right? You can have a homework problem or an exam problem where I'll ask you to derive this. This is true for any gas, right? I did not assume anything about ideal gas in doing this. But this is a powerful relation because it allows you to connect one property with another property, all these strange properties. Before today's class, you would not have thought. I mean, it's clear that before today's class, most of you were not thinking about thermal expansion, right? Because you say it's not taught in middle school. I have to take your word for that. Okay, fine. But this is interesting because it's giving you a connection between heat capacity and thermal expansion coefficient, right? Which is kind of strange. Why should such a connection exist? Why should there be anything? And so you can think about it the other way. If you could calculate the heat capacity for a material by doing some by constructing a calorimeter and measuring how the heat capacity looks, and you could calculate the thermal expansion coefficient and the volume, and you come up with a model for the internal pressure, you can go and calculate how does the internal energy change with temperature. So this is abstract. This relation is something I don't expect you to remember. What was the take home of deriving this relation? The take home was that in thermodynamics, once again, you can connect one partial derivative to another partial derivative and connect different chemical properties or material properties to each other. Next time, we are going to start thinking more about enthalpy. And just like for internal energy, our variables that we worked with were volume and temperature. What variables do you think we should be looking at when we think about enthalpy? P, right? Pressure and temperature. There is nothing stopping us from thinking about enthalpy also as a function of volume and temperature. It can be done, but this will be a more intuitive way of looking at enthalpy. I'm trying to avoid to use the word natural way of looking at enthalpy because later we will talk about natural variables. But for now, this is our just intuitive way, and that's what we will do